Okay, so we're going to have lecture number 3 on Organic 1, and we spent some time last lectures looking at the structural theory, at valence, and at indices of hydrogen efficiency. I'll do one more of the indices of hydrogen efficiency questions, just to kind of walk you through a couple of options, and then we move on to today's topics. So let's imagine I ask you to draw isomers of formula, say C7H7NO2 Cl2. So what I would do, and again, we can't import this formula as it is into the calculation of indices of hydrogen efficiency, because that formula is predicated on hydrocarbons. You're comparing hydrocarbons. So what I need to do is to convert this formula into one that is sort of the equivalent hydrocarbon. And to do that, I'm going to ask, how do I handle each type of heteroatom? And by type, we're looking at the valence. So for monovalence, if you remember, we're going to add 1 H per heteroatom. For divalence, we just ignore them. For trivalence, we subtract 1 H per heteroatom. So the way I will handle this is for the chlorine, I would have, because I've got 2 chlorines, I'm going to add 2 H's, and that'll be C7H9NO2. For the O's, because they're divalent, I'm going to ignore them, and that becomes C7H9N. And for the N, because it's trivalent, that becomes C7H8. So I'll subtract 1 H for the N. Now, you can choose to do this on the exam or not. Or you can just do it mentally, right? So I'm going to add 2 H's, that's 9, ignore that, that's still 9, subtract 1, that's 8. And just write C7H8. So you don't have to do this rigmarole on paper to get to the answer. If you can do it in your head, that's fine. You can do it in the exam in scrap or on the exam, that's perfectly fine. But once you get to the equivalent hydrocarbon, you want to compare that formula against the corresponding alkane. And by corresponding, we mean the alkane, CnH2n plus 2, that has the same number of carbons. So the generic formula for an alkane is CnH2n plus 2. So having 7 carbons, that's C7, so it's corresponding. H, 7 times 2 is 14 and 2 is 16. So I'm going to subtract, the carbons go out, which they must, and I'm missing 8 H's, which correspond to 4 pairs of H's. If I have 4 pairs of H's, then that's my HDI. My HDI or my IHD is 4. That's my index. I do not require you on the exam to tell me all the permutations of 4 HDIs, because it's too many, okay? But you should have those in your head, and if the question gives you no guidance as to what isomers you draw, you just draw what you want, and you can localize them to one subtype, or you can spread them out. So I'm going to instead ask you to draw isomers that, one, have a benzene ring, so have a benzene ring. I'm going to ask you to draw one that has a carbonyl group, and 3 is a nitrile, and 4 has exocyclic double bonds, 5 is bicyclic. So I'm going to draw 5 isomers. And what will happen very often on the exam is that I will tell you, and in fact, I'll tell you, draw isomers that have particular units in them. And so part of it determines the skill, but also your recall of certain features, certain groups. So the benzene ring, if you remember, is going to have carbon, carbon, carbon. It's a 6-membered ring that has alternating single and double bonds. So I can go double, single, double, single, double. That's my benzene ring. And that consumes all 4 HDIs and 6 of my 7 carbons. Well, I've got another carbon, an N, and 2 O's and a Cl. I'm going to go ahead and populate this structure with those features. And guys, I could do this in 1,000 ways, right? I can have a C here, and the N here, and an O here, and another O here, and the Cl's there. Or I can put them all together, the CO. I mean, it really doesn't matter. It really doesn't matter. So I'm just going to go and say, why do I do that? I'm going to put the carbon here. I'm going to put the N here. I'm going to put 1 O here. Let's stick the other O on it. I've got 2 chlorines. Why don't I just stick the 2 chlorines on the N? Right? And that takes care of my carbons, of my HDIs, and of my heteroatoms. The 1N, my 2 O's, and my 2 Cl's. Hey, 2 Cl's. Okay, so now all I need to do is to populate it with the H's. So I obviously there are no H's on these because the valences are already satisfied. I can do H, 1, 2, 3, 4, 5, 6, 7. And everybody has the valence is satisfied. So that is one of literally probably 150 isomers that have a benzene ring. I mean, and it's probably more than that. Draw one that has a carbonyl group. Well, if you remember, we talked about this last time, a carbonyl group is C double bond O. So I know it has to have C double bond O. I'm just going to go ahead and draw C double bond O. Okay, great. That only uses up 1 of my 4 HDIs. And it's up to me now how to spend the other 3, because the question gives you no direction. I'm just going to make my life easy and try to suck them up by putting in a triple bond, for example, because that takes up 2 HDIs. And then maybe I'll do a ring. Why don't I do a ring, which is another HDI? Or I could have done, 2 double bonds. I could have done, if I have 3, I could have done, 3 rings, a double bond and 2 rings, 2 double bonds, any number of things. The question gives me no direction, so I'm going to use what I want. So I'm going to go ahead and say, so 1, last. I'm going to go ahead and say, so that C is a carbon here with a triple bond here. So that's 1, 2, 3 carbons. And I'm going to go ahead and try to put a ring in. So let's say 1, 2, 3. I've got 4 more carbons. I'm going to say 1, O, N, C. So 1, 2, 3, 4, 5, 6, 7. And I've used, so 1, 2, 3, 4, 5, 6, 7 carbons. I've used my 1N. I've used both O's. And I've consumed 1, 2, 3, 4 of the HDIs. So at this point, all I want to do is stick in the H's. I'll have 1 H here, 1 H here, that's 2, 3, 4, 5, 6. Oh, wait a minute, something is weird here. So 4 HDIs. 1, 2, 3, 4, 5, 6, 7. 1 and 2 O's. I forgot my CL's there. So you see, I was about to end up with 1, 2, 3, 4, 5, 6. Would have been 7, 8, and 9. But I don't have 9. I only have 7. So I knew something is funny. So it tells me I did something weird. I forgot the CLs. So if I'm going to go ahead and put the 2 CLs here. And then I'm back to 1, 2, 3, 4, 5, 6, and 1, 7. That would work. I could have done any number of things with this structure. Then I want to do one that is a nitrile. And if you remember, a nitrile has a carbon triple bond N. And if I know it's got a carbon triple bond N, just put it in. So why don't we go ahead and just get some room up here. So I know it's got a nitrile. And I'll put that in. So it's got a C triple bond N. Well, that consumes, good God, that's great. So C7H7 NO2 Cl2, right? C7H7, yeah, that's right. So I've got a nitrile that consumes 1 carbon, 1 N, but 2 of my HDIs. I need 1 more HDI, I need 2 more HDIs. I could have that as another triple bond. For example, I could do that. So I can do another triple bond here. And I prefer, if it doesn't give me any more boundary conditions, I just try to knock them off early. So just take care of my HDIs and move on. Or I could have done 2 rings or whatever I wanted to do. So at this point, I have all of my 4 HDIs accounted for, right? 2 in each triple bond. I've got my N, I've got 1, 2, 3 of my carbons, and at this point I know there's nothing else waiting for me. There's no ring, there's no double bond, none of that stuff, because I've spent them. So 1, 2, 3, I'm going to go 4, 5, 6, 7 of my carbons. I need O's. Just for the heck of it, I'm going to go ahead and stick, what do I put it, just for variety, I'm going to put an O here, and then a C, and then an O. So that's 1, 2, 3, 4, 5, 6, 7 carbons, 2 O's, 1 Cl, 2 Cls. Doesn't really matter. So if I do that, I've taken care of my 4 HDIs, my 1, 2, 3, 4, 5, 6, 7 carbons, my lone N, both O's and both Cls. At this point, it's just H's now. So I have 1, 2, 3, 4, 5, 6, 7, and we are done. So that's a nitrile. And my compound could be a nitrile and something else. So this is a nitrile and it's got an acetylynic group. Well, that's okay. The question didn't give me instruction with that part. It just said it had to be a nitrile. In the same way, they said it had a carbonyl group. It gave me no indication of what the others are. So that's my job, to just fill in the blank as I see fit. It needs to have then now an exocyclic double bond. So exocyclic means outside of the ring. And it really, in a sense, means it's coming off of the ring. So this tells me 2 things are needed. I need a ring, that's why it's cyclic, and it needs to have a double bond. So that already tells me 2 of my 4 HDIs are going to be consumed. It doesn't give me any indication of how big the ring needs to be. Does it have to be 7 carbons? Does it have to be 7, 8, 9? Does it have to be 5, 4, 3? That's entirely up to you. Now, I want to make a point here while we're on it. So this is a ring. But this ring contains only one kind of an element. It's only got carbons. If I have a ring that only contains one kind of an element, the ring is said to be homocyclic. Right? Homo means the same, so it's a ring that contains the same kind of elements. In fact, if I wanted to be really anal about this, I can say the ring is carbocyclic, meaning that the element in the ring, the only element in the ring is carbon. That's different from this kind of ring. Because this kind of ring contains different kinds of elements. I've got carbons, I've got O, and I've got N. If your ring contains different types of elements, 2 or more, it is said to be a heterocyclic cyclic. It is said to be a heterocyclic. Hetero means different. So rings may be homocyclic, and they could be all N's, all O's, all carbons, right? Or rings can be heterocyclic, and they contain at least two types of atoms. So we want to have an exocyclic double bond. So I'm going to go ahead and I'm going to erase this one. So I'm just going to erase them both. So I'm going to say, in fact, so I'm going to make this one, I'll do one of these that's homocyclic, I'll do one of those that's heterocyclic. So I'm going to change the question a little bit. So 4 part A, a homocyclic, 4 part B, a heterocyclic. Well, so I'm going to go ahead and just put, I've got 7 carbons, let's do 4 of them in a ring. So it could be 3, 4, 5, 6, 7. I'm going to go with 4. So I'm going to have carbon, 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 carbon. It tells me it wants an exocyclic double bond. I'm going to go ahead and satisfy that immediately. So put a double bond coming off the ring. That's what exocyclic means. Now, this is very important. If I have a ring that looks like this, and I have carbon, and then a double bond here, that's not considered exocyclic, right? Exocyclic means you're coming off the body of the ring. Okay? So you're not an appendage, you're coming off the body of the ring. So I have 5 carbons, and I've exhausted 2 of my HDIs. I've got 4 HDIs left, and so I'm going to go ahead and say put a carbon here, another carbon here, so that's 5, 6, 7. I need an N and 2 O's. I need 2 more HDIs. Why don't I go ahead and satisfy those HDIs with a carbon-oxygen double bond? And what the heck, let's do why don't we do a bond to a nitrogen and do a nitrogen-oxygen double bond? Why don't I do that? So now I have 1, 2, 3, 4 HDIs. I have 1, 2, 3, 4, 5, 6, 7 carbons. I've got 1 N, I've got 2 O's. I need 2 chlorines, let's just spend them here. And so all I need now are just to put in H's. So where will my H's go? Let's follow the valences. I'll have 1 H here, and then 2, 3, 4, 5, 6, 7, and we are done. So homocyclic with an exocyclic double bond. That's all my instructions were. I fill in the blank as I see fit. Let's do a heterocyclic. I'm going to go ahead and say carbon, carbon, carbon. Why do I put a nitrogen? What the heck? Put an oxygen here then. Right, so I can do that. It's going to have an exocyclic double bond. So why don't I put a double bond here? And let's put that to, who do I have left? Let's put it well, it has to be the double bond, to a carbon. So a carbonyl, so C double bond O would not be considered an exocyclic double bond. It has to be carbon-carbon, right? That's important. So this is now 1, 2 HDIs. I'm going to spend my other 2, I'm going to spend them quickly. So 1, 2, 3, 4 carbons. I'm going to say 5, I'm going to spend it here. So 1, 2, 3, 4, 5, 6 carbons. Let's put the other one here, I'll make it 7. 3, 4, 5, 6, 7 carbons. I've got 1 N, I needed 1 more O, so I'm going to put an O here. And then I need CLs, let's stick them on here. So this is 1, 2, 3, 4 HDIs. 1, 2, 3, 4, 5, 6, 7 carbons, 1 N, 2 O's, 2 CLs. At this point now I stick in the H's. So I'll go 1, 2, 3, 4, 5, 6, 7. So this is a heterocycle with an exocyclic double bond. Those were my instructions. And I just filled in the blank as I saw fit. I want a bicyclic. Bicyclic simply means that there are two rings. The rings may be connected or they can be separated. It doesn't tell me whether the rings need to be heterocyclic or homocyclic. And even in the bicyclics, I could say I want a homobicyclic, right? Which means all of the atoms in the bicycle have to be one element, which will have to be carbon in this case. Or I could have a heterobicyclic, which means that at least one of the rings has two different types of atoms. Question didn't say, so I can do whatever I want. So I'm just going to go ahead and cut to the chase. Why don't we do a carbon, 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 and then let's do a carbon, nitrogen, oxygen, oxygen. Right. So this is 7 carbons, 1 N, 2 O's. I need I have 2 HDIs. I need CLs. This looks like a good place for a CL. I need 1 more CL. I need 2 more HDIs. This looks like a good place for an HDI right here. And who the heck cares? I can put another HCl, another HDI there, another double bond. So I've got 1, 2, 3, 4 HDIs. All of my carbons, 1, 2, 3, 4, 5, 6, 7. My N, my 2 O's, my 2 CLs. I'm just going to populate the N's now, which will be 1, 2, 3. Well, there's 1 here too. So 1, 2, 3, 4, 5, 6, 7. And we're done. Okay? So you will get the hang of this, and in fact you must get the hang of this. It is simply a matter of knowing, given the formula, how to manipulate the formula into the equivalent hydrocarbon. Then using that, and that requires knowing what to do with the heteroatoms, and then importing that hydrocarbon into the HDI calculation using the corresponding alkane, the same number of carbons. Once you identify the number of HDIs, you know what structural features you have, or you're allowed, and then you follow the mandates of the question, if any, and you just draw them. Keep in mind the valences. And the way you do it is you put in your carbons and your heteroatoms and your HDIs, you get that taken care of, and then the H's, just you plug them in and it has to work. Okay, so what we'll do now is look at some stuff that you would have seen. This part is recap. You'd have seen this in Gen Chem. And if you took chemistry in high school, you'd have seen bits of this as well. What we will talk about it briefly here, because it's an important foundation for much of what's the formula. So we're going to talk a bit about bonding, right? Bonding. Yes. So ionic and covalent bonding. So the way I tend to do this is to say that the reason that elements bond is to acquire a noble gas configuration. The noble gas configurations for elements depends upon which period the element is in. I may have done this on the first lecture. If you are, this is energy levels now, if you're in energy level 1, then all you have access to is the 1s orbital, and so that, like all orbitals, can only hold 2 electrons. So for you, your noble gas configuration is a duplet, right? Because at this point, the first shell is full. If you are a second row element, you have access to the 2s and the 3 equivalent 2p orbitals. Each of those can hold 2 electrons. And so for you, a noble gas configuration is an octet. So the octet rule is nothing special, right? It is one of, well, there's seven periods, so it's one of 7 rules, right? We could have been hopping on the duplet rule. The reason we hop on the octet rule is much of the chemistry that we look at deals with elements in the second period. If you are a third period element, you obey the 18F rule. There's no nice name for it before that. Although there is a particular stability associated with 8. So the reason elements bond is to acquire a noble gas configuration. So let's for a minute ask ourselves what happens when we react lithium metal with fluorine gas. So lithium and F. Now fluorine technically is F2, but I'm going to look at it as if it were an F, a fluorine atom. So fluorine is element 3, lithium is element 3, fluorine is element number 7, has an atomic number of 7. So lithium has 2 electrons in the first valent, in the first shell, and 1 electron in the valence shell. That's how I spend my 3, right? So it would be for lithium, right? For lithium, I would have 3 electrons, and I would go 1, 2 to fill the first shell, and then 3. So lithium can be written either as, I can write lithium's configuration either as 2, 1, 2, 1, or I can say it's 1s2, 2s1, so the 2 electrons in the 1s orbital and 1 electron in the 2s orbital. Right? Those are equivalent depictions of lithium. Or I could be more graphic and draw something like this. There are 2 electrons in the first shell and 1 electron in the valence shell. They're all equivalent depictions. Fluorine has 7 valence electrons. So I've got 1, 2, 3 accounted for. According to Pauli exclusion principle, I will pair the electron. That's 4, 5, 6, 7. Okay? So I've got, that's 9. Number 9. Yeah, fluorine is 9. So that's 9. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. That's kind of silly. Alright, so fluorine I can write as 2, 7. That's what was stuck in my head. So 2 in the first shell, and then 7 in the second. Or I can write it as 1s2, 2s2, 2p5, right? So these are my 2p's. So 1s2, 2s2, 2p5. Or I can be more detailed and say it's 1s2, 2s2, 2px2, 2py2, 2pz1. So I can break down the distribution within the individual p orbitals as 2 in the x, 2 in the y, 1 in the z. 2 in the x, 2 in the y, 2 in the z. And the only reason we call them, we have them organized that way is that we read, at least in the West, we read left to right. So we call this by convention x, y, z. Okay? Or I could draw a graphic representation and have draw something like this and say 2 here, 1, 2, 3, 4, 5, 6, and 1 is 7. So this is lithium. Well, what is that? This is lithium, and this is fluorine. Okay. Now, neither of these atoms has a filled valence shell. The valence shell is the outer shell, right? Lithium only has 1 electron in the valence shell. Fluorine has 9. Neither one of these elements has a noble gas configuration. So they're on the hunt to become stable. They will undergo chemistry with the intent purpose of acquiring stability at the end of the process. The reason elements undergo chemistry The reason the elements bond is to acquire a noble gas configuration. So for a minute, let's diagnose what are the options available to lithium, right? So lithium then has two options. Either lithium can decide to gain 7 electrons, because as of now it only has 1, and if you're in the second period, for you a noble gas configuration is 8 electrons. So if you have 1 electron in this shell, what you want, one option is to gain 7 electrons and become 8. So lithium could gain 2 electrons and gain 7 electrons and become 2,8. But what would happen is lithium would have a charge of 7 minus. Now, chemistry is lazy. Chemistry takes the path of least resistance. If I gain, now, and you don't gain n electrons all at once. You gain them one, then another, and so on. Same way, when you lose electrons, they aren't all lost in one blurry process. They're lost sequentially. So you can imagine lithium gaining 1 electron and becoming lithium minus. Okay, fine. You're not an octet yet. You now have the task of forcing another electron onto a negatively charged particle. Electrons repel each other. So although there was some work in putting on the first electron, there is more work in putting on the second. There's even more work in putting on the third, because now you're putting on a negative electron onto something with a 2 minus charge. So the repulsion is massive. Even if you get to 3 minus, and there are a few particles that make 3 minus, putting on another electron to something that is 3 minus is essentially impossible. Nobody has a charge greater than 3, well, very few particles have a charge greater than 3 minus. Because the work involved is too much. So we find another way around it. So putting on 7 electrons to become 7 minus, that is too much energy required. That is a non-starter. So what's the other option? The other option is just go ahead and lose the 1 valence electron, in which case you end up with a noble gas configuration that's simply 2. And you are now lithium plus. So lithium was posed 2 choices, both aimed at getting a noble gas configuration. Gain 7 electrons, that's too expensive. Too much work involved, and chemistry is lazy. The other more viable option is simply lose the 1 electron and get a noble gas configuration. So this is what lithium does, right? The path of least resistance, less work involved. Fluorine, which was 2,7, also has 2 options. And what are the options? Go ahead and gain 1 electron and become 2,8. Right. Gain 1 electron and become 2,8. In which case you're now F minus, because I'm gaining 1 electron, so I'm going to acquire negative charge. Or I could lose 7 electrons and become 2. If I lost 7 electrons, I would become F7 plus. So fluorine has 2 choices, as most of the elements do: gain or lose. Well, when I lose 1 electron, because electron gain and loss are sequential processes. When I lose 1 electron, I become positively charged. To become 2 plus, I must now rip a negative electron out of a species that bears a positive charge. Well, that's going to be hard. Certainly harder, because electrons and positive and negative charges attract. So if I'm already positive and I have to rip away a negative electron, I am ripping it away against a significant force of attraction. But let's say I could do that. So I rip out the electron. I am now 2 plus. The act of pulling off an electron from a particle with a 2+ charge is going to require a massive amount of energy. And even if I could make 3+, the act of pulling off an electron from a 3+ particle requires so much energy, it never happens. Because chemistry looks for the path of least resistance. It doesn't want to do a massive amount of work. So pulling off 7 electrons, that is a non-starter. So what fluorine will do is to take the path of least resistance and gain 1 electron. So what determines whether I win, whether I lose or gain electrons? And the answer is where you are in the periodic table. If you are on the left, so you are lithium, beryllium, boron, so carbon, nitrogen, oxygen, fluorine, and neon. So this has 4, right? This is group 4. If you have 1, 2, or 3 electrons, surely the better option is to lose 1, 2, or 3 rather than gain 7, 6, and 5. Right? To acquire noble gas configuration. So if you're on the left, your chemistry is defined by electron loss. That is the easier path to noble gas configuration. If you are on the right, now the noble gases are what you're trying to aspire to. If you are on the right, it's better, it's easier to gain 1, 2, or 3 rather than to lose 5, 6, or 7. So elements that tend to lose electrons all are on the left of the periodic table. At least the main group elements. They're on the left. Elements that tend to gain electrons are all on the right, and it makes perfect sense. But elements that tend to lose electrons have certain properties. They tend to be shiny. They tend to be excellent thermal conductors. They tend to be excellent conductors of electricity. All because of their affinity to lose electrons. And there's some chemistry and physics behind that. We call elements that tend to lose electrons, we call them metals. So metals tend to form, metals tend to associate naturally on the left of the periodic table. Elements on the right are non-metals. They react in exactly the opposite way. They gain electrons. And essentially down the middle are elements that don't lose or gain electrons. They tend to form other kinds of bonds. Because losing or gaining 4 is just too much. Right? And in a perfect world, the metalloids would have been straight down the group, but chemistry is an exercise in exception. Okay, so with all of that, what happens when we react lithium and fluorine? Well, they agree then to transfer electrons. Because we cannot lose electrons into space, nor can we grab an electron from space. So what happens is the lithium atom loses an electron to form lithium plus, and fluorine atom gains the electron lost by lithium to form F minus. So what we have is electron transfer. These are 2 half reactions describing the favored process, the only process, for those elements. And in the end, the lithium transfers an electron to the fluorine, and I end up with an ion pair. Okay, positives and negatives attract. So there's a force of attraction that now arises between the lithium plus and the F minus. And what this force of attraction does is it causes the elements to assemble into a lattice in which each ion is surrounded by what's called its counter ion or its Gegen ion. So for example, I'm just going to put this here. So what's going to happen is each lithium ion forms a force of attraction to So each lithium ion, so each lithium ion has a force of attraction to the fluoride ions around it, and each fluoride ion has a force of attraction to the lithium ions around it. So I will say that the lithium cation is surrounded on all sides by its counter ion or by its Gegen ion. Gegen is a German word for opposite. It is not Gegen. So the Gegen ion and the counter ion are equivalent terms. I'll make 2 points. I've drawn this in 2 dimensions. So the lithium is surrounded on the left, right, top, bottom, as I have it. But there is a fluoride in the front and then a fluoride behind the board. So you can imagine the lattice displays one up or one down, if you will, or one left or one right. It doesn't really matter. So I'm going to have the lithium surrounded on 6 sides by fluorides. I'll have the fluoride surrounded on 6 sides by lithium plus, right? Top, bottom, right, left, front of the board, and then behind the board by Li minus. This dashed line represents the force of attraction. The force of attraction is the bond. That's what a bond is, right? I've got a bond to my wife and to my kids. That is a force of attraction. You're bonded to your pets. It is a force of attraction. And the force of attraction between oppositely charged particles, between ions, that force of attraction is called an ionic bond. So the ionic bond is the bond, the force of attraction, that arises between cations and anions, between counter ions. Okay? Now the ionic bond is very strong, and it's very strong for several reasons, and we'll get to those in more detail later on. So that is the nature of the ionic bond. And ionic compounds tend to form crystalline lattices, crystalline compounds, because they form ordered lattices. We'll expound on that some more later. Okay, that's great. Well, what happens then to the elements that don't have the option of losing or gaining electrons? And the answer is, what they will do instead to acquire noble gas configuration is to share electrons. So I'm going to imagine, and I'll pick fluorine because I've already talked about it on the board. So if I draw a fluorine atom, right, 1, 2, and I have 1, 2, 3, 4, 5, 6, and that's really sort of a cartoon version because we know atoms don't have skins or membranes, right? These are all very diffuse electron clouds. Although fluorine has the option of simply gaining an electron to become F minus, that process only occurs if there's somebody, a metal, who can give it the electron. Because for me to gain an electron and become F minus, which gives me a noble gas configuration, I need an electron donor. But I don't always have those. I don't always have metals. So 2 fluorine atoms, right? Why the size is so different. So 2 fluorine atoms could very well coalesce, right? This is F with my 1, 2, 3, 4, 5, 6, 1 electron, and then 1, 2, 3, 4, 5, 6, and it's 1 electron. They could very easily coalesce to form something that we will draw like this. And for now, I'm going to ignore the valence shell, the cores, and I'll have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and then 2 electrons being shared here, this one and that one. Put it this way, another representation, an equal representation. I'll have F, 1, 2, 3, 4, 5, 6, F, 1, 2, 3, 4, 5, 6, and then 2 electrons being shared between them. Well, there is a nucleus here, and a nucleus here. And I'm going to ignore, I'm going to ignore these for a minute. and just focus in on the nuclei. So these two nuclei are mutually attracted to that electron pair. We talked about that, I think, in the first lecture, right? That the covalent bond is the mutual attraction of the nuclei for the shared electron pair. And I think I gave you guys a story about Mary. I call them Mary and John. I remember that now. Although one's name is, her name is actually Mary. But right. So I have a positive nucleus attracted. Attraction is a bond attracted to those electrons, and these electrons are simultaneously attracted to that nucleus. So what we then get is a force of attraction between the nucleus and the shared electron pair. That force of attraction is the covalent bond. So a bond is a force of attraction. If you notice, the forces of attraction, the bonds, are always between something negative and something positive. That could be a cation and an anion, sure. Or it could be a nucleus and the electron pair that is shared. Right? Between nuclei and the shared electron pairs. Okay, so covalent bonds then happen between non-metals, which it will have to. Because if fluorine, so fluorine has two choices, right? Because it can't lose 7 electrons. It can gain 1. But to gain 1, it needs a metal, because the metal has to lose electron. So if I have two non-metals, neither of whom can lose electrons, the best thing to do is just to share. So covalence or covalent bonding involves the sharing of valence electrons. Ionic bonds involves the transfer of valence electrons, right? The exchange of valence electrons. Okay, to a very large extent, we're going to ignore ionic bonding for most of this course. We will come back to it once or twice, but since organic chemistry is a chemistry of carbon, and those compounds typically have hydrogens and nitrogens and oxygens, we're dealing with elements that are non-metals. So the type of bonding that is king is covalent bonding. So although we've introduced ionic bonding, which we've met before, we're going to kind of ignore it for the rest of the series. We come back to it in reference once or twice. But that is really the purview of inorganic chemistry. For organic chemistry, we are more concerned with covalent bonds. So we want to talk a little bit about some of the features of covalent bonding. And what we're kind of interested in for now are the factors that affect the strength of a covalent bond. Well, we wrote this inequality on the board a while back. The F is the force. So this is not fluorine, this is force, right? Is proportional to the charges on the species over R squared. So F is the force of interaction. Q would be the charges, the charge on the particle. And R is the internuclear separation. Literally the length of the bond, right? So if I have, so my bond length is that distance. That's what I call R. R is the internuclear separation. That's the bond length. Now, a couple of housekeeping things. This equation is very general. This inequality is general. F is the force of interaction. When these are the same sign, plus, plus, in other words, two positively charged particles, or two negatively charged particles, the interaction is repulsive. When they are opposite charges, the interaction is attractive. So F, the force of interaction, could be interpreted as the repulsive force between particles, or for our discussion, the attractive force between the particles, or the bond strength. Right? The bond strength. So you will notice then that what this tells us is, as the charge on the, so for the purpose of bonding, I'm going to make one of these things Q plus and make one Q minus, indicating that the charges are opposite signs, and that we're only looking at bonds, right? Forces of attraction. So the bond strength, the force of attraction, rises with the charges on the particles and with the decreasing size of the distance between them. And we talked about this on day one, right? The reason carbon forms strong bonds is because carbon is small. And for two small atoms, the bond length, right, is short. For large atoms, right, for large atoms, the bond length in the nuclear separation is long. And why is that important? Because it means you are miles away, is that a 7? You're miles away from the electrons. Okay? So this distance is large. If this is large, then that number is small. And it gets small in a hurry, because that's r squared. So as the bond gets longer, as r goes up, right, F gets smaller very rapidly. So what are the factors that affect the strength of a bond? Well, the bond length, which really comes down to the size of the atom. Small atoms make short bonds make strong bonds. The other thing is the charges. And what for us directly makes an impact is the number of electrons in the internuclear gap. The number of electrons in the internuclear gap. For example, we know that carbon can form a single bond, carbon can form double bonds, carbon can form triple bonds. Great. Every bond represents 2 shared electrons. So what this really means is that between these 2 carbon nuclei, there are 2 electrons in that bond. Between these 2 carbons, there are 4 electrons. Between these 2 carbons, there are 6 electrons. So Q minus for a triple bond is larger than Q minus for a double bond, larger than Q minus for a single bond. And if you raise Q minus, you raise F. There's a linear relationship. So bonds get stronger when the atoms are smaller, and bonds get stronger when the bond order increases. The bond order basically is the number of bonds, or the number of bonds. So this is a single bond, a double bond, a triple bond. So as the bond order increases, there are more electrons being shared in the internuclear gap. So the force of attraction between the nucleus and those electrons goes up. If I have 2 electrons, my force of attraction is a certain number. If I have 4 electrons in the gap, well then the force of attraction is greater. If I have 6, it's greater still. Now, it turns out it's not twice. A double bond isn't twice as strong as a single bond. And a triple bond isn't 3 times as strong as a single bond. Because it turns out the electrons are in orbitals that aren't the same. And so their properties are slightly different, and that impacts the strength of the bond. So it's not as if a double bond is twice as strong as a single bond. And we'll cover that in some more detail later. So the factors affecting the strength of a bond are the R, which is determined by the sizes of the atoms. Small atoms make stronger bonds. Right? Small atoms make short bonds are strong bonds. And by the bond order, the number of electrons being shared between the atoms, and by extension, the number of bonds being formed. Okay, we're going to talk a little bit, again, and this is a concept you've seen in Gen Chem 1. We're going to talk about Lewis structures. But we're going to approach Lewis structures in a little bit different way than you would have seen in Gen Chem 1. But it's based upon exactly the same concepts. And, you know, we're going to look at this in some measure of detail. So I'll begin by saying that, and so we're looking at Lewis structures. And I'll begin by saying that much of the essence of chemistry is electron motion. In fact, physicists often refer to chemists in an attempt to be derogatory as electron chasers, because we want to figure out where have the electrons gone, what have the electrons done. And for those of you who take Organic 2, a good third of Organic 2 involves how do the electrons move when chemistry occurs. We call it the mechanism of reaction. We do a little bit of that in Organic 1 as well. So it is critical for us to understand how and where electrons move from point A to point B. And for us to have a good sense of that, we need to be taking inventory of electrons in the reacting particles. And the way we do that is by looking at the Lewis structures of the particles that are reacting, right? Because we can identify particles that have a large amount of electron density, that are electron rich, and particles that have a small amount of electron density, that are electron poor. Because ultimately, chemistry, which is the science of electron transfer, chemistry happens in one direction. Electrons move from something electron rich to something electron poor. That is the essence of chemistry. And by the way, that concept is not a foreign concept, right? Nature hates imbalance. Nature likes everything to be even. Right? Nature does not like what are called potential differences. Right? That potential differences require energy to be maintained. Nature doesn't like that. Nature likes things to have a potential difference of zero. And we know that, right? If I put a hot object in contact with a cold object, they don't stay that way. There's a potential difference. So heat flows from hot to cold until they're at the same temperature. If I have a region of high pressure and a region of low pressure, that's not good. Winds will flow from high to low pressure. That's in part how we get tornadoes and so on. If I know a lot of chemistry and you don't, information flows from me to you to equalize the potential difference. So whenever there's a potential difference, something moves in order to minimize or eliminate the potential difference. It is the nature of the universe. So in chemistry, electrons flow. And how will they flow? From a region of high electron density to a region of low electron density. Well, how do I know who's high and who's low? And the answer is, I look at the inventory of electrons. We call that the Lewis structure. And if I look at the Lewis structure, it'll tell me, am I electron rich or electron poor? And I can then make intelligent assessments of how chemistry is happening. Of if it will happen, how it will happen. So I'm going to write for you a definition of a Lewis structure. I will never ask you to define it, right? But you should have a working definition for Lewis structure. So a Lewis structure provides the number and arrangement of all atoms